Welcome, this is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium. This conference would not have been possible without our sponsors, PQ Shield, SSL.com, Entrust, Keyfactor, HID Global, and the organizational support of the Post-Quantum Cryptography Working Group of the PKI Consortium, and in particular, Entrust, Keyfactor, and Logius. Would you like to join the PKI Consortium? Go to pkic.org/join, or contact us if you would like to become a sponsor.
It's my pleasure to introduce to you Dr. Mila Anastasova, is that right? Oh, right, I got one right, finally. I told you I'd get something right by the end of the conference. And Dr. Anastasova is with AWS. She's an applied scientist. She brings a cutting-edge research in optimizing both classical and post-quantum cryptography algorithms. Her work focuses on making these complex algorithms practical for the various platforms. So, welcome.
Okay, thank you for the great introduction. Yes, my name is Mila Anastasova. I'm an applied scientist at Amazon, and today I'm going to present the project, the impact of ML-KEM and ML-DSA on mTLS connection, Time-to-Last-Byte. This project is a collaboration with the principal security engineer, Panos Kampanakis, who just presented an amazing topic. In this presentation, we're going to focus on answering three main questions. First of all, we're going to go to a brief introduction where we're going to discuss the importance of post-quantum mTLS. Later on, we're going to see how to estimate the cost of migrating to post-quantum mTLS, or the estimation cost for migrating to post-quantum PKI. Finally, we're going to see some performance results that we have obtained through our benchmarks, where we're going to analyze different performance graphs. First, we will start by discussing why post-quantum mTLS is important. And in particular, we're going to see why migrating to post-quantum ML-KEM and ML-DSA is important. As we know, quantum computers threaten to, the increasing capabilities of quantum computers, they threaten to break the classical crypto systems that are deployed nowadays. This is the reason for NIST to initialize a post-quantum standardization process in the year 2016, where last year, in 2024, the final standards, including ML-KEM and ML-DSA, were announced. Starting this year, 2025, until 2027, the Commercial National Security Algorithm Suite, CNSA 2.0, requires to set post-quantum standards as default and preferred algorithms for cryptographic applications. Starting the year 2030 until 2033, as we have already heard multiple times during this conference, the CNSA 2.0 requires the exclusive use of post-quantum algorithms standards. Okay, after seeing why the post-quantum migration is important, let's see why mTLS is important. As we know, to do so, we're going to focus on one particular use case of post-quantum cryptography, in particular the network security protocols. As we know, TLS, transport layer security, is widely deployed. It is used to establish connection with secure websites via HTTPS, for public APIs, and many other applications where only one of the communication parties is being authenticated. On the other side, mutual TLS, or mTLS, it is used in scenarios where mutual trust of authentication is required. Some of its applications include microservices communications, internal APIs, edge-to-cloud communication, zero-trust architecture, basically where both communication parties require authentication. Most importantly, while there are many studies that discuss the post-quantum migration impact on TLS, there is actually very little studies, very little research on the impact of ML-KEM and ML-DSA on mTLS connection. This is the reason for us to focus on evaluating the cost of post-quantum mTLS. To understand the difference between both network protocols, we're going to discuss the communication flow. On the left-hand side, we can see the TLS 1.3 handshake, where basically the client initiates the connection, sending a client hello message. After that, the server sends a server hello message containing a key share, allowing an encryption key, a shared secret, to be derived among the communication parties. Or actually, in the server hello message, the server is also going to send his own certificate and certificate verify messages, which are going to allow to confirm the identity of the server, or in other words, is going to allow him to authenticate in front of the client. Finally, the client ends the TLS handshake by sending a finished message, and after that, application data can be exchanged between the communication parties in a secure way. On the right-hand side, we can see the mutual TLS handshake communication flow, where similar to the TLS connection, the client is going to initiate a connection, where both communication parties are going to send their hello messages. Additionally, the server is going to send the certificate request message, and respectively, the client is going to respond with his own certificate and certificate verify messages before finishing the connection, where, of course, at the end, application data is exchanged in a secure way among both authenticated communication parties. Okay, now that we have seen the importance of post-quantum migration and the details of the mTLS handshake protocol, let's see its performance estimation, or bless you, or in other words, let's see how we're going to estimate the post-quantum mTLS latency overhead. To answer this question, to see how this is done, we're first going to see how a secure network connection is established. To do so, we're going to again follow the communication flow graphical representation. First of all, a TCP network three-way handshake is executed to connect both communication parties. After that, the mTLS handshake is performed, as we have already described it, in order to finally allow application data transfer. Even though a secure network connection is established through a sequence of network protocols, it actually can be divided. It is actually divided in a number of round trips, each round trip being a two-way communication flow. It is important to say that round trips are expensive. They feature high latency, which is also referred to round trip time, or RTT. In order to reduce the number of round trips, multiple messages are actually merged together up to a given size and are forming part of a single round trip. In order to visualize how data messages are being transferred, we're going to make the analogy with a bucket of a given size, where messages are placed and are sent all together in a single round trip. After that, later on, we're going to redefine the term bucket with its technical, corresponding technical term. However, for now, we're going to focus on answering the question how post-quantum mTLS or how post-quantum PKI is going to affect our communication latency, or in other words, is it going to introduce additional round trips? To answer this question, we're going to now focus on estimating, on seeing how the cost of secure network connection is estimated, or in other words, how to estimate the round trip time or the number of round trips. First, we're going to look at the communication flow in the scenario of classical crypto primitives. As we know, they feature small key sizes and signatures, which easily fit into a single bucket, or in other words, form part of a single round trip. In order to visualize the communication flow cost estimation, we're going to focus again on the graphical representation. First of all, a TCP handshake is executed, requiring one round trip. Later on, the mTLS handshake is performed. Based on the fact that client hello and server hello messages consisting of key share, certificate, and certificate verify messages fit into a single bucket, the entire mTLS handshake is going to require a single round trip until its completion. After that, application data can be sent at additional cost, of course. Let's see, however, what is going to happen when messages that are sent exceed the size of our bucket, or in other words, what is going to happen if they cannot be transferred in a single round trip. Well, in this case, the sender is going to send one bucket of data. After that, however, he's going to be blocked, waiting an acknowledgement from the recipient, from the client, until another bucket is being sent, or in other words, before being able to continue the communication flow. In other words, this means that additional round trip is going to be introduced. This is indeed the case of post-quantum crypto primitives. We know that they feature large key and signature sizes. Therefore, post-quantum elements, in particular post-quantum certificates, they're not able to fit into a single bucket and therefore are going to introduce additional round trip. Again, focusing on our graphical representation, we can see the estimation of post-quantum secure network connection as, again, a one round trip for the execution of the three-way TCP handshake. For the execution of the mTLS handshake, however, again, one round trip is going to be needed for the client hello and server hello messages. The fact that the server hello, again, consisting of key share, certificate, and certificate verify, is going to exceed the size of our bucket is going to require an additional round trip to be added. In other words, the server is going to send the first half of its certificate in one bucket. After that, is going to be blocked until an acknowledgement is received from the client before being able to send the second data bucket in additional round trip. Therefore, another round trip is being introduced. In the exact same way, on the client side, the client certificate and certificate verify messages, they exceed the size of the bucket and again introduce an additional round trip. Let's see, however, so far we discussed in general how we're estimating the cost of classical and post-quantum network connection based on the same scenario. So let's see, however, how we're going to estimate this cost accurately based on the current trends in technology. In order to do so, we're going to introduce the term congestion window. Or in other words, we're going to redefine the bucket from our previous slides with its corresponding technical term. In particular, congestion window is defined as the amount of data that fits into a single round trip of around 15 kilobytes of data. Post-quantum certificates are estimated to be around 22 kilobytes, which, of course, they do not fit into a single congestion window of around 15 kilobytes. Therefore, as we have already seen, they're going to introduce an additional round trips. Let's see, however, what is going to happen when, instead of focusing on decreasing the size of the message, we focus on increasing the size of the congestion window. Well, in this case, in a congestion window of around 34 kilobytes, post-quantum certificates are going to easily fit into a single round trip. Therefore, they're not going to introduce an additional round trips. Focusing again on our graphical representation, we can see that in this case, the server hello message, again consisting of key share, certificate, and certificate verify, is going to fit into one congestion window, therefore is not going to introduce additional round trips. In the exact same way, the client certificate and certificate verify messages are going to be transmitted into a single round trip, eliminating additional round trip times. Finally, we can see that for the execution of post-quantum mTLS, it's going to require actually the same number of round trip as classical mTLS protocol. And it is actually important to mention that the application data transfer is also going to benefit from these large congestion windows, of this increased congestion window. In other words, it is going to improve the customer experience or the time to last byte. This is actually the reason why nowadays a lot of servers tend to set their congestion windows to larger values. Okay, now that we discussed how to estimate the cost of post-quantum mTLS, let's see now what the actual results are. We're going to start by discussing the mTLS handshake, where first of all, we're going to discuss the classical crypto primitives. For this benchmarking, we have used elliptic curve Diffie-Hellman for the key establishment and RSA for as digital signature algorithm with around 3.5 kilobytes of certificate sizes. In other words, in this graph, in this slide, we're going to discuss the classical, in other words, small certificates, considering a small congestion window sizes. On the left-hand side of the slide, we're going to follow the communication flow as we have already discussed it in order to introduce the different round trips. And on the right-hand side, we're going to see the corresponding latency in milliseconds, where we're going to represent the median, the 15th percentile, and the 19th percentile over 1,000 samples. This data, this slide, represents the data that we have collected running at 100 megabits per second network speed and with a round-trip time of around 50 milliseconds. Finally, we're going to say that the round trips we're going to denote by a horizontal line in our slides in order to see how exactly and where these round trips are being added. Okay, starting with following the communication flow, we can see that first the TCP handshake is performed, which on the graphical representation, we see that it adds 50 milliseconds of latency, and it is marked with a red horizontal line since it adds a round trip. After that, the mTLS handshake is performed, where basically, again, based on the fact that classical small certificates, that they fit into a single congestion window, the entire mTLS handshake is going to require a single round trip for its completion. After that, additional application data can be sent, again at additional cost. In this slide, however, in our graphical representation, we can see that actually there is an additional data, the actual data transport latency added for transporting the key share, the certificates, and certificate verify messages, which is in between 4 and 6 milliseconds. Now we're going to focus on the mTLS handshake, however, considering post-quantum crypto primitives. In other words, we're going to compare classical small certificate sizes, marked in blue color in our graphical representation, with post-quantum large certificates of around 22 kilobytes, as we have already seen, marked with red color in the graphical representation. In this slide, we're going to see what is the performance considering small congestion windows. And as we can see, as we discussed, actually, post-quantum certificates are going to exceed small congestion window sizes. Therefore, they're going to introduce an additional round trip. We can see that, in particular, post-quantum mTLS is going to introduce of around 52 milliseconds of latency, of performance overhead, which is around 50% of performance drop. The same scenario we have evaluated with in the case of slow network speeds of around 1 megabit per second, again with 50 milliseconds of round trip, where based on the larger sizes of the certificates, we can see that more significant latency overhead is introduced of around 115 milliseconds, which is around 83% of latency overhead performance drop down. Let's see, however, how the actual mTLS handshake performance looks like. Again, let's compare classical and post-quantum certificates, this time considering large congestion window sizes. As we have discussed, both classical and post-quantum certificates are going to fit into a single large 34 kilobyte congestion window. Therefore, they're going to require a single round trip for their transportation. This shows in the graph where basically we can see that the performance of classical and post-quantum mTLS is very similar. In more detail, we can see that the performance overhead when introducing post-quantum mTLS is of around 2 milliseconds, which corresponds to around 2% of latency overhead. On the right-hand side, we can see the same scenario, the same scenario evaluated at 1 megabit per second speed, where again the performance drops significantly based on the large sizes of the certificates. Again, the performance overhead is estimated to around 83% of latency performance drop. It is important, it was important to see how the handshake itself is going to be impacted by these large certificate sizes. However, in the real world, connections are actually opened with the aim to transfer application data. So let's see how the actual mTLS performance is going to look like when we focus on transferring around 50 kilobytes of data, where we have 50 kilobytes of application data. In this case, we can see that the performance is actually increased. The latency is increased based on the larger amount of data that is being transported. However, we can see that the overhead, the latency overhead introduced by post-quantum mTLS remains significant, relatively small, around 3 milliseconds, which represents around 1.4 latency overhead. The same scenario at lower network speed is presented on the right side of the graph, where we can see that post-quantum mTLS is going to introduce around 230 milliseconds of overhead, which corresponds to around 35% of performance drop. Finally, let's see how our performance is going to look like, considering larger transfer data, larger amount of application data being transferred of around 150 kilobytes. This is actually a common scenario in today's heavy communication. So we can see that the performance is going to again, the latency is going to again be significantly increased based on the larger amount of data that is transported. However, the difference, the latency overhead of introducing post-quantum mTLS is going to remain relatively small, of around 3.5 milliseconds, corresponding to 1.3% of latency overhead. The same benchmarks measured at slow network speed show around 230 milliseconds of latency overhead for post-quantum mTLS, which corresponds to around 15% of performance drop. As a conclusion, we can say that post-quantum mTLS, based on ML-KEM and ML-DSA, it is indeed going to increase the number of round trips needed for its execution when considering small congestion window sizes. However, when increasing the congestion window, we have seen that post-quantum certificates or post-quantum mTLS is going to allow us to be executed, to be performed in the same number of round trips as classical certificates. Therefore, the main overhead of post-quantum mTLS depends on the network speed. As an example, we can see that around 18 kilobytes of larger certificates, post-quantum certificates, at 100 megabits per second are going to introduce of around 1.6 milliseconds of overhead. Of course, for mTLS scenario, this overhead is doubled, resulting of around 3.2 milliseconds of overhead. It is important to also say here that application data is usually much larger. And finally, as we have seen, the mTLS handshake, or in other words, time to first byte, is going to be impacted significantly by introducing post-quantum mTLS handshake. However, the user experience is usually related to time to last byte, or in other words, when the application data that has been requested is received. Therefore, as we have discussed and we have seen, the overall impact of post-quantum mTLS is going to be decreased based on with the increase of the data that is being transmitted. Okay, well, thank you.
Excellent. Okay, questions, and I've got to bring the mic up. Here we go.
Okay, thank you. You assumed a 22K byte client certificate. In my experience, they should be a bit smaller because they're not web PKI certificates, but directly issued certificates.
It may be the case. The thing is, the most important is if they're rather smaller or larger, the size of the congestion window, particularly for this study, because we focus mainly on how many round trips are going to be needed for the execution.
But if they cut it down to maybe 10K or so, it should fit within the congestion window, which means you lose a round trip.
Yes, exactly, which is actually even a better scenario. The thing is, we wanted to. It's a very good question, actually. The thing is, we wanted to stress that because of it's going to actually also improve the application data transfer. A lot of already TCP setups, network setups, are considering larger congestion windows independently of the crypto-only applications.
So in the slides that you said the ML-KEM was 768. Just curiosity on your 22 kilobyte certs, what was the ML-DSA? What size was it?
We considered ML-DSA 65 in our in these cases, but
so I mean,
but it can vary again. Like the main impact, the main stress in this talk was to discuss how the congestion window is going to actually ease the.
Yeah. No, I was curious whether. So at that size, even if you went up to the bigger one, to ML-DSA 87, you would still fit within your larger congestion window.
Exactly.
All right, thanks.
Hi, thank you for the presentation. Quick question, out of curiosity, have you tried to enable zero RTT and then try to see how the metrics differ? I know that it's susceptible to replay attack. In many cases, it's considered as a security concern to enable zero round trip, but have you ever tried?
We didn't consider, actually the opposite. We have considered large RTT just to make sure that our performance benchmarks are correct, but with zero RTT, we have not considered this scenario.
Okay, thanks.
Great presentation, Doctor. Thanks for that. Just have a quick question. So the congestion window concept is at the transport layer, right? It's not an implementation on TLS itself.
Yes, it is a good observation. It's in the on the TCP. It's a TCP setup.
Right.
So it's not related directly to the TLS itself. It's not part of TLS at all.
Right. So what's the workaround? Were you guys able to resolve by modifying like the TCP stack, or?
Yeah, well, actually, the measurements that we have taken are based on emulation. We emulated that basically locally. So we set the congestion window to. We were able to just set up our own because we were the server and the client at the same time. Right. So we were able to set both of the congestion windows to the size that we want to.
Gotcha. Okay, so you can modify those. And the second question I had, sorry, Chris.
Of course.
The application data you showed in the last like 2 or 3 slides, 50 kilobytes, 150 kilobytes. Like, what was the reference to that? I've been trying to understand because the application data continues post handshake.
Yes, the reference is that actually the handshake is going to be very significantly impacted by post-quantum, especially post-quantum certificates. The thing is, when we increase the data that is being sent, the time-to-last-byte, how the user experiences this slowdown is becoming less important because he's actually waiting for application data. The user experience is based on when I request something and when I actually receive it and I see it. Let's say on my screen, or like when I receive the data that I'm waiting for. So the impact, the overall impact of, let's say, heavier handshake is going to be to reduce with a larger amount of data that we're transporting, that is being waited for.
Thank you very much. Wonderful. Thank you.
How do you get to a quantum-safe state? That depends on the current state of your digital security infrastructure, as well as your level of visibility, control, and automation over those systems. Check your level of preparedness with the Entrust Post-Quantum Readiness Assessment. Whether you're already on the path to quantum safe or just beginning your journey, Entrust can equip you with the right knowledge and solutions. There are many paths to a quantum-safe future. Secure yours by taking the Entrust Post-Quantum Readiness Assessment today.